In 1.11, we're looking at the descriptive measures for populations. We've looked at descriptive measures for samples already, and the first thing you see right here under the population mean is what we learned earlier about our sample mean, and that is indicated by this x bar equals sigma x sub I over lowercase n. The x bar is the sample mean, the lowercase n is the sample size, and then the x sub i's are all your individual data points. The population mean, I can get them both here on the same screen, looks very similar. Notationally, though, it is different because when we look at statistical studies, we want to be able to determine, is this a sample or is this a population? So if you see x bar, you know that it is a sample because that's the sample mean. If you see the lowercase mu, that is the population mean. So x bar, sample mean, mu is population mean, and capital N is the size of your population. So we're still calculating it the same way. When you have a population or a sample, the mean is still computed exactly the same. You add up all the observations, divide by the size of the sample or population, and that gives you the mean. It's just a notational difference to indicate, well, actually to differentiate between the two types of data that you're evaluating. So the first example that we have is the Augusta National Golf Course. The name of each hole derives its name from a shrub or a tree that's associated with it. What we're interested in, though, is finding the population mean length of the holes at Augusta National. Since we're listing all 18 holes on that course, this is a population set. It's not a sample. If we were looking at, say, golf courses across the United States, then the 18 holes at Augusta would be a sample. But because we're only focused on Augusta National as our area of study, every hole at Augusta, we're taking into consideration that makes it the population of that particular study. So to find the mean of that population, we'll just go over here to Google Sheets. I get tired of saying Google Sheets a lot. I get tired of saying Google a lot. It's getting aggravating. Teaching has become weird. Anyway, so here are all the holes. I've already listed them. And all we want to do is find that mean or that average. So we're just going to select equals, average, and then we will type in, or select rather, all of the lengths of each hole, and we get 413.055555. So it's going to be repeating. So let's just, and if you recall, I believe it was 2 days ago, we looked at the rounding properties for statistics. We always round one decimal beyond the data that we're given. So this will round to 413.1. So the mean, in this case, I need to get rid of the highlighter, mu is equal to 413.1 yards. And again, recall that the units are important. So there is a big difference between x bar and mu. We just need to make sure that notationally we're using the right symbols when we do these problems. The population standard deviation. So we've looked at the sample standard deviation, and that's what you see here in the middle of your screen. Remember the sample standard deviation, that's the computing formula, and we're using Google Sheets to do all of our computations. But it still would be nice to maybe attempt one or two problems using these computing formulas just to get an appreciation for how they're calculated. But the sample standard deviation is indicated by the lowercase s. The population standard deviation is indicated by the lowercase sigma, and the computation is still the same. You can see a couple of the differences here. I can't fit these both on the same screen, but we have s equals sigma x sub I minus x bar over lowercase n minus 1. In the population, it's sigma of x sub I minus mu, so that's the population mean, divided by capital N, which is the population size. And when we take the square root of all this, we get our standard deviation for the population. There's also a computing formula for this that you can use if you want to do these by hand, and that's the sum of all the observations squared divided by the size of the population minus the square of the mean, or the population mean, and then you take the square root of that and you'll get sigma, or the population standard deviation. For example 2, it says calculate the population standard deviation of the lengths of the holes on Augusta National Golf Course. Now, when we did sample standard deviation, I showed you how to do that using sheets. For population, it's going to be the same thing. Remember, we're going to type in STD. I know that's weird, but type in STD, and it's going to bring up this option. So you have standard deviation.p, standard deviation.s. Standard deviation.s is when you're doing a sample standard deviation. When you want to do a population standard deviation, select standard deviation.p, select your values, and hit enter. So our standard deviation for the lengths of all the holes at Augusta National is 130. Well, that would round to 132 yards. So we'll go ahead and put that down. We get still on the highlighter. Sigma is equal to 132 yards. All right. Now, there's two other terms that we want to introduce today that you'll hear from time to time, and we need to be sure that we understand the difference between what these two terms mean. When we hear the term parameter, it is a descriptive measure of a population. When we hear the term statistic, it is a descriptive measure of a sample. So when we look at some of the terms that we've already picked up so far, mu and sigma, that's the population mean and population standard deviation respectively, those are parameters. X bar and S, that's the sample mean and sample standard deviation, those are statistics. The next thing we want to cover is the standardized variable. So this is something that we're going to use a lot. You're going to hear about z-scores, and we'll talk about those a little bit more in the next couple of sets of notes, and I'm going to provide you with a table that you're going to want to, hopefully, if you have an opportunity to print that off and hang on to it. Any of these tables that I'm going to be providing with you guys as we go through the class, you certainly probably want to try to print them off if you can, so that you can have them as a resource when you're doing your assignments or even when you're taking tests. So the standardized variable, if we have some variable x, we introduce a new variable called z. That's the standardized version of x, or we also may call it the z-score. And it's simply calculated by taking an observed point, in this case x, minus the population mean divided by the sample, or the mean, the standard deviation of the population rather, and that's going to give you the z-score. We're standardizing everything so that we can compare these values across different populations if we need to. And again, this will make more sense later. Right now, we're just worried about making sure we understand how to calculate these things. We'll get into more detail with them shortly. A standardized variable always has a mean of 0 and a standard deviation of 1. So when we standardize these things, every variable we can make have a mean of 0 and a standard deviation of 1 by standardizing it. So the first thing we want to do is consider in example 3 some variable x, and it has these values: -1, 3, 3, 3, 5, 5. They've already provided us with z values of -2, 0, 0, 0, 1, 1, and part A simply asks us to determine the standardized version of x. All that is taking this formula and substituting in what we know. So for the standardized version of x in this case, it's z equals x minus 3 over 2. And I probably should point out, I jumped ahead of myself. I probably should point out I've already done this. I didn't indicate, I thought I had in the notes here, but the mean, the population mean here is 3, and the standard deviation is 2. That's how I already knew though. But if you want to verify that, we can go back over here to sheets. This column, I have my x values, so if I want to calculate the mean, remember it's going to be the average. You can see that that is 3, and if I want the standard deviation, dot P, highlight my values, and we get 2. So there's where those numbers came from. I thought I included them in the notes and I didn't, so I apologize for that. So you just substitute those in, and this equation that we have written here for part A, that is the standardized version of X. Part B, find the observed value of Z corresponding to an observed value of X equals 5. We can look at our table and see that anytime X is 5, Z is 1, but let's use the formula to just verify that. So we have Z is equal to our observed value of 5 minus 3 over 2. 5 minus 3 is 2. 2 over 2 is 1. So we get a Z-score of 1. Part C, calculate all possible values of Z, all possible observations of the variable X. Or, jumping ahead. Calculate all the possible observations of Z. So we would just apply that formula, and what we would end up with is the second row in Z. We could, or in this table. So what we could do is if we substitute in -1 into this, so -1 minus 3 is -4. -4 divided by 2 gives us -2. You don't have to calculate these because I've already provided them, but that just gives you a little extra practice should you decide to try that out. So if we tested 3, we put in 3. 3 minus 3 is 0. 0 over 2 is 0, and that corresponds to the Z-score that we find right here. Part D, find the mean and standard deviation of Z. Is it necessary to do these calculations to obtain the mean and standard deviation? Let's go ahead and first calculate the mean and standard deviation. Hopefully you guys are already screaming at me, no, don't do that. We already know what it is, but we're going to do it anyway. So the mean is average, and we highlight our values, hit enter, it's 0. Standard deviation, highlight our values, and we get 1. We did not have to do that because if you recall from the notes, standardized variable always has a mean of 0 and a standard deviation of 1. So this just provides you with a way of checking to ensure that you are computing the right values. If you create a table of Z values and you check the mean and standard deviation, if it's anything other than 0 and 1 respectively, then there is an error somewhere and you probably need to go back and check your data. Now, if it's, say, the standard deviation is 0.999, that could be a rounding issue. But if it's really off by quite a bit, then you know that there's probably an error with your data somewhere. For part E, it says show dot plots of the distributions of both X and Z, and then interpret the results. I'm just going to kind of draw a really quick dot plot here. I'm not going to go through the steps because you all are very familiar with, I hope by now, how to do this. Let's see, observations go up to 5, -1, -2. Uh-oh, my pen stopped working. There we go. -3. So we're looking here at the distribution of X, and we know that 3 is our mean, and our standard deviation is 2, so 1 standard deviation to the left of this mean, and then 1 standard deviation to the right. And if I put in my points, I have 3 of them, 3 observations at 3, I have 2 observations at 5, and I have 1 observation at -1. If I do the same thing for my Z-scores, let's see, -3, -2, that is a 3, I promise. -1, 0, 1, 2, 3. We don't need to go above we don't need to go below -3 or above 3 to the right, because typically we're going to see 3 standard deviations in any case. We know that the mu sub Z, so the mean of our Z-scores is 0. 1 standard deviation to the left, 1 standard deviation to the right. If I put in my observations, I have 3 of them that are at 0, 2 are at 1, and 1 is at -2. So there's my dot plots. That's really quick and rough. But the interpretation is they show how standardizing shifts a distribution so that the new mean is 0, and it changes the scale. we look at the one in blue, and that's just our observed values. And that scale could be really large. Anytime we standardize a variable, its scale will always be -3 to 3. We won't have these really large observations, and the spread won't be as much. It refocuses the center of our data at 0, and then it allows us to compare some of this information a little bit more easily. So there we're talking about z-scores, and when we talk about z-scores, it's the observed value of a variable x. That corresponding value, z, we call that the z-score, and or the standardized score, and that tells us how far from the center that particular observation is. So if we look at example 4, part A, find and interpret the z-score of juniper's length of 180 yards. So we just substitute that into the formula. It's 180 minus 413.1, that's the population mean, divided by 132, which is the population standard deviation. And when we compute that, 180 minus 413, we're going to get approximately -1.77. For part B, I'm going to interpret these for you in just a second. For part B, it's 495 minus 413.1 over 132. And that's going to correspond to a z-score of approximately 0.62. So what this tells me for part A is that the length for juniper is approximately 1.8 standard deviations to the left, or 1 point standard deviations below the mean. And the z-score for camellia is approximately 0.6 standard deviations above the mean. And that's all you have to do for these interpretations. Those numbers tell you how far above or below the mean we're looking. And then part C, it says to construct a graph showing the results obtained in part A and B. We know that the mean, the population mean, is 413. We also know that the standardized variable mean is 0. And then if we go one standard deviation to the right, using the population standard deviation, that's 132 yards. So we would add 132 to this value. We would get 545.1. And similarly with the z-score, that's one standard deviation above the mean. One standard deviation below the mean is 413 minus 132, so we get 281.1. And that's one standard deviation below the mean. If I go 2 standard deviations below the mean, that takes me to 149.1 yards. And I can plot these 2 points in here now. So the part A, juniper, is 180 yards, and it has a z-score of -1.77. So that's going to fall right in here. I'll put J for juniper. Camellia is 495 yards, and it's 0.62 standard deviation below the mean. So if you compare the two scales, here's our x values, and then here's our z values. You can see how standardizing this correlates to the population itself. That's why standardizing these variables is very important, because then we can compare two populations that we are looking for particular characteristics of to see if they share these characteristics. When we standardize the variables, it shortens our scale, allows us to only focus on the deviations from the mean rather than the overall size. If we create a scale for the golf course, we could have a very large scale from 0 yards to, say, 600 yards. But when we standardize it, we always will have a scale from -3 to +3. So that is the conclusion of this second set of notes for today, and you guys can read through that. That just kind of goes, that's a little bit more information about the z-score and descriptive measures for populations, but that's just for you to look at when you get a chance. There's your homework problems. Again, use Google Sheets when possible. Put this stuff into a Google Doc. There, I said Google 3 times now in the last minute. So this assignment has 8 questions. So you have 4 from the previous set, 8 from this set, 12 questions, and you get a whole week to do it. If you guys have questions, let me know, and I should be seeing you in class here in just about 8 minutes. I'll talk to you guys soon.